Beautiful. All right. Hey, well, thanks very much. I'm Jeff Dyck, Director of Engineering from Mentor, and I was formerly from Solido Design Automation, which was a startup that was founded back in 2005. And we've been working on active learning as a way of solving problems that are hard to solve and improving SPICE coverage. I'm just going to share my video here, share my screen out here, and jump into a presentation. All right, so what I want to share with you is a class of algorithms that we've found incredibly useful at Solido and now at Mentor for increasing coverage by a lot. And I think it's not just a class of algorithms that's suitable for SPICE. I think it's suitable for all kinds of problems, and I think it generalizes really well. I'm going to talk a little bit about SPICE specifically in this talk, because that's where we live. But definitely, one of the takeaways is that these methods, I think, generalize really nicely. So the problem that we've run into in the SPICE verification world over the last decade is this really huge explosion in what needs to be verified. So we've got now safety critical applications, which require a lot more demonstration of margin, a lot more demonstration of coverage. So that would take a lot more simulation if you just had to brute force it out. With FinFETs, we got this much wider voltage domain. So we used to just, simulate 3 voltages and we were done. And now there's, 8 or 10 that people will often simulate. There is also multi-patterning, which is modeled in multiple extraction conditions from our extraction tools that also need to be simulated. So that's increased the scope a lot. Tighter product margins is important. So a lot of our customers are saying, the cost of manufacturing's gone up, competition's increasing, especially for high volume products. They just don't want to over margin. You can't get away with over margining as much as before. And getting tighter margins requires a lot more precise verification data. And then one of the biggest ones too is in timing analysis, we have to do something called characterization, which is creating timing models. And that used to not be statistical. We could just, we just add a fudge factor for variation effects, and that was too big. So we went to a statistical timing approach a couple of years ago, and that just exploded the simulation counts for something that was already quite expensive. So, what this has turned into is we've got way more process voltage, temperature, now extraction condition type corners. If you're looking at typical planar types of processes, we'd have 5 process, 3 voltage, 3 temperature. There's maybe 45 corners there. You might simulate a subset of those. With FinFETs, it's common to have hundreds of corners now. So we're kind of 5 times more conditions to cover. With statistical variation, we've gone from 3 sigma verification and sign off for a lot of chips to 4 or 5 sigma for safety critical type applications. We've also with replicated components like standard cells, we've done this for memories for years, but for standard cells and other types of components that are frequently used in replication on chips, people are actually verifying these to High-Sigma. And if you look at the math there, it's really unfortunate. We used to be able to run a few thousand simulations to verify the 3 sigma. If you want to go up to 4, 5, 6 sigma, we're talking orders of magnitude more simulation if you had to brute force it out. And then with statistical characterization, we're looking at if you had to brute force it out, also over 100 times more simulation. So just a phenomenal increase. Not a little linear increase. This isn't 2 or 4x. This is orders of magnitude more simulation that would be required. So the problem that we ran into is that brute force SPICE verification methods simply can't deliver the coverage required within production runtimes. And what happens when we've got poor coverage is we end up, first of all, with this endless engineering debate. I've been in the middle of lots of these with customers, and I know that lots of them happen outside of the discussions that I'm in, but just we can't cover everything, so what should we actually simulate? What should we pay to cover? There's a lot of back and forth on this and philosophical debate that happens. one of the strategies is just to brute force it out. So let's buy extra CPUs, let's buy extra licenses, and let's see, if this is something that that we can brute force out. Let's also extend the design schedule. This really sucks. No one wants to extend the design schedule, but this sometimes happens to get more coverage. But the problem is that we're not just looking at simple linear growth that can be compensated this way. What happens is we still end up with poor coverage, and we've still got lots of design and manufacturing uncertainty. And then what designers do is they go back to over-margining, because chips need to work, right? So you give up power, performance, and area, and still we run into some yield loss and some catastrophic failure. So it's not something that we can really just scale up and brute force out. The right solution direction is actually more of an algorithmic solution approach, where there are a bunch of algorithms that are on the shelf that can help toward this problem. This is stuff that we started building out at Solido in 2005, 2006, 2007. We started looking into algorithms like this as ways to improve coverage, and we looked at things like better balanced samplers, like Latin hypercube and lattice rules. The idea there is if you can just distribute random samples better than randomization can, you can decrease the number of samples you need. There's stretch sigma samplers where we take our input distributions and we stretch those out, and then when we sample from them, we actually get out to high sigma faster, which is cool. There's more classes of algorithms like importance samplers and worst case distance methods and most probable points, which are nice, fast, accurate, best effort high sigma methods. There's stuff like recursive statistical blockade, which can get us out to high sigma faster. And then there's supervised learning techniques where you go and train a machine learning model on some existing data and then use that model to predict new data. And what happens with a lot of these algorithms is they've got a whole bunch of limitations. And this is something that, we ran into when we were trying to deploy early products that use these types of techniques back in the mid-2000s and late 2000s. And you find these big limitations. And what it amounts to is really these four main problems. A lot of the solutions that are algorithmic don't generalize very well. We can demonstrate that it works on 3 cases in the lab, can write a great paper from that. You go run it on something that's a little different. It doesn't really work so well and can give you the wrong answer. So I see a lot of algorithmic approaches, both in academia and in industry, that I categorize these as fake general solutions, where they look general, they look like they work good on some cases, but proof by lack of contradiction isn't a proof, and we see a lot of these types of algorithms. Also, we see ones that are unreliable. You can get an answer, but it might be wrong. It's usually right, but it might be wrong, and it can't tell you. So if it's a pessimistic answer, what you end up doing is over-margining accidentally. If it's optimistic, this is even worse, because now we think that our chip works fine, but it actually doesn't, and you get yield loss or catastrophic failure. Some unreliable algorithms will say, well, I'm not really sure. It's good. At least it knows it's not sure. It doesn't give you an answer. That's better than being wrong, but you might not have a different way to solve the actual verification challenge, so you're kind of left in a hard place. We've got unverifiable algorithms. One of the things that, if you go and tell someone, hey, I sped this up by 1,000 times and I've got an answer in just 1/1000th of the simulation as it would have taken, they'll ask you, prove it, prove that that's right. And that's often really hard for people to do. All these algorithms are guilty till proven innocent, and so we need really good verification types of techniques that are efficient and can be done within design cycles as well to prove our work is correct. And then a lot of these algorithmic approaches are difficult to use. So, they take manual tuning. You have to look at the results and say, did this work or not, and possibly iterate with different tunings. And so it takes quite a bit of expertise. And what we did at Solido is we realized that, algorithms with these kind of traits, they don't productize very well. You can't deploy them well to large numbers of designers, and they don't really work that well in real engineering types of environments. What we ended up coming up with is a whole suite of of products that use active learning as the key ingredient for speed up. So what these do, and I'll get into how this works in just a second, but what the nice benefits are is you can cover the entire space. You can actually get these exponential or order of magnitude speed ups that we need. And what we tend to see is the larger the space gets with the more variables there are, the more we can save with these types of approaches. So it's not a linear savings. It scales with the scale of the problem, which is really good. That's what we want in order to cover exponentially or order of magnitude larger spaces. It also can minimize simulation. So this is the other thing that we want is instead of simulating too much stuff that we don't really need, it's going to be really, really picky. This class of algorithms is really picky about what it's going to simulate and can just simulate the absolute minimum that it needs in order to get the right answer. It can target areas of interest, so not all circuits have the same problem that we're looking at. If we're looking at DC gain on an op-amp, high gain's usually okay. We want to see low gain, so let's go and focus on areas of low gain, or let's focus on areas that are interesting. If you've got a temperature inversion, let's go find the vertex of that temperature inversion. Or if you've got a low voltage drop-off where you see nice delay behaviors, and then you get to low voltage and there's a knee, let's go find that knee explicitly. So we can do that kind of thing with active learning approaches dynamically. And then what we want to do is provide really good guesses, quality engineering type guesses at the rest of the information. So if you simulated all the right, the most critical information, you've got perfect accuracy where it matters the most, and then you can actually do guesses, deliver guesses that are within a target accuracy. I mean, that's an ideal answer. You haven't wasted any simulation. You've got great guesses throughout the space, and you know exactly what's going on where you care the most. So that's why we like these classes, this class of solution, the active learning approach. I'm going to go over the way that this works. So what we start off with is we don't know anything about your circuit. Sometimes we can take historic data and we can roll it in as long as what you're looking at now behaves similarly, but a lot of the time it doesn't really carry over that well. So what we do is start with an initial design of experiments to learn something about the circuit that's under test here. So we're going to simulate just a small amount of the total space. Maybe this is 1% or 2% or even less in a lot of cases. We're just a small percentage here, as little as we possibly can to start learning about the main effects and the interaction effects. So the interaction effects in this space are really, really important, and you need to shake those out too. So this is a really lean design of experiments. Then what we do is we take that simulation data from that initial design of experiments, and we build an accuracy-aware machine learning model, supervised learning model typically. And the really important thing here, accuracy-aware is super important because what a machine learning model is a guessing machine. You build a guessing machine, and a guess is only useful if you know how accurate that guess is. And we're going to use that accuracy later in the algorithmic approach to do some really cool stuff here too. But we're going to build an accuracy-aware model. Now, it's not going to be very good yet. It's going to have only been built from that design of experiments data. It's not going to be really refined in areas of interest. It's going to not be refined in areas where things are changing, those low voltage drop-offs and so on. It's not going to know where those knees of the curve are, but it's going to give us a general idea of where that stuff is happening. So we can take our supervised learning model, and then what we can do is say, let's predict the entire space, get answers for the entire space, and then start diving into the areas of interest. So, that DC gain on an op-amp example, we can start looking at the area where there's low DC gain predicted by the model. So we can actually go through and start running low DC gain points, which is really cool. So now we're running simulations where we actually care instead of through the whole space where we don't care about most of the results. And then where this becomes active here, we're actively already selecting stuff that matters, but we can go back, we can take this new data that we've run at the tails, at the areas of interest, and take that back and then refine our supervised learning model. So now we can take the data that we have from the initial design of experiments and then the stuff from the areas of interest, and combine that to create a model that's got a good general idea of what's going on for our circuit and really, really good information where we care the most. So now our model's hyper accurate in the areas that matter. And that's really cool. We can do this multiple times. We don't just get one shot at this. We can say, well, don't stop until we've actually got, the area of interest is really stabilized and our guesses there are as good as our actual simulation or really, really close. So we can do this multiple times if we want. The next step is called model building optimization. And what the goal is here is to make the rest of the predictions adequately accurate. So we've got perfect accuracy in the areas of interest already. What we want is the rest of the space to have good guesses. Let's say we want to be within 2% or something like that. Well, let's keep going and running cases with maximum uncertainty until we hit that 2% accuracy goal. And we can also, take the information now that we've simulated in these areas of greatest inaccuracy and put it back into the model. So we can circle around, do this more than once if we need to, and now we've got a model that's got perfect data in the areas of interest, and it's meeting our target accuracy everywhere else where it's delivering guesses. Last step here that's really important is the self-verification step. So imagine yourself, as a design engineer going into a design review and saying, hey, I covered this massive, massive space with just a smattering of simulation, and everyone looks at you and says, well, how do you know that that's right? Well, what we want is for our algorithm to automatically go and do that work for them. So, create a method that's better than what any human would ever want in terms of a proof and run that. And if the self-verification actually fails, we don't want it to fail because it means that the rest of our algorithm didn't work out so well, so it's bad if we get down here and it fails. But you can actually go and take that data back and say, hey, let's try this again and recover. So that's kind of neat too. Usually don't have to do that if the algorithm's designed well, but it is a way of recovering. And then the last step here is we've just learned a lot about how the circuit works, so we can actually take all of that knowledge of how the circuit works and responds and so on and share that with the designer so that they can have insight into their circuit's responses and helps them with debugging, sometimes optimizing circuits. So kind of a useful flow in general. So this is what active learning looks like. What we've done over the years is we've built one major tool set here. It's an active learning verification tool set called Variation Designer. And this has been in the industry we introduced it originally in 2008, 2009 kind of time frame. And we've been incrementally improving this. And every single tool, except for one, every single tool in this tool set is an active learning solution. That's its magic trick for getting really, really good speed ups, really reliable results. So it's pretty mature. It's been around for well over a decade now. We also started working on the timing characterization space. We've got a couple of products in that space that we've developed out that use similar tricks to speed things up a lot. I'm going to talk a little bit about those here just to give you an idea of how a few of the pieces in here work. The benefits that we've seen, though, I think this is really, where the rubber meets the road, massive speed ups. I was talking about before how, the space has exploded exponentially or by orders of magnitude. Well, if you look at the numbers, the speed up numbers we can deliver with these approaches, we are in that orders of magnitude space. And it actually is completely compensated for the explosion. We're running similar amounts of simulation as we were without all the problems I started by explaining. Without the more PVTs and without all the High-Sigma Monte Carlo charges and so on, we're running similar amounts of simulation. We've won all of that back while still giving really reliable answers and in highly usable tools. With ML Characterization Suite, we can actually generate new Liberty models at new PVTs, new process voltage temperature combinations, about 1,000 times faster than a characterizer can, so that's really good. And we save about 50% of the schedule with this approach. We can also find new classes of errors in Liberty data. I'm going to talk about that, and reduce Liberty debug time really, really substantially from weeks to hours, which is cool. The things that are really good about these active learning approaches, they are general. Because the techniques actually go and actively learn, about the subject, it can actually really adapt to a lot of different types of responses. It's a very flexible type of algorithm that you can make, that you can adapt to just about anything, which is really good. It works really quickly. We do get that orders of magnitude faster result. It's an accurate approach. It can give you perfect answers where it matters the most in your areas of interest, you know, your worst case DC gains, for example, instead of your best case. It can just focus in on the area of interest, which is really good. It can give you accuracy-aware guesses elsewhere, automatically checks its work, can recover when it's wrong, which is really interesting. And because the algorithms in this class here are really, they're really adaptive, you know, we're actively learning, we can adapt to problems, it means that it takes the burden away from the user. It doesn't require a bunch of expertise in machine learning algorithms or fancy algorithms to use. You can just push go and the thing figures out how your circuit works, which is really cool. I'm going to zip forward a little bit and talk about a couple of the newer things that we're doing. So in 2018, we released a new algorithm called PVTMC Verifier. And this is the first time that we had actually combined the PVT corner problem and the Monte Carlo problem into the same active learning tool. And what we're able to do here is pretty cool. Every one of these distributions that you see in this example, every one of these, there's 45 different probability density functions here. And every single one of these that you see is a different process voltage temperature condition. And every single one of these is going out to 4.1 sigma in this particular case. And if you actually ran all these simulations, you'd end up running 45 million simulations. This particular case, it ran 1,299 simulations. So less than you'd run for a single 3 sigma Monte Carlo analysis at a single PVT corner. We're now getting out past 4 sigma and across every single corner with a really, really nice accuracy. And what you can see here is there's some of these are shown as solid lines, some of them are dashed lines. This is one of those DC gain type cases. What it's doing here is it's saying when we're close to the bad side, when we're close to low gain, let's actually run more stuff and verify all this and then produce really good estimates for stuff that's in the higher gain space. So we're not wasting simulation to verify high gain. We don't really care. That's usually a feature. But for the low gain cases, we are running extra simulation and focusing in there. But in this particular case, about 30,000 times faster. So we're making up that time. Really nice tool for that. Some of the main advances here that I think are significant. First of all, just the fact that we're doing active learning across both corners and Monte Carlo at the same time is useful. You can make gains on both sides, so why not multiply them together in a single analysis? That's push buttons. That's the main thing. There's a new type of algorithm that we have here. We call it ordinal class optimization, where we're taking the PVT corners and then categorizing them. It's a categorization classification type technique where we actually put them together in groups that behave similarly statistically that we can model as groups. So that gives us about a 10x speed up across PVTs compared to not doing that. And then we've got a thing called a vector sampler, and this is kind of like a smart stretch sigma sampler that actually calculates error, models error, corrects error adaptively. So you don't keep increasing your confidence interval as you stretch more. It actually goes and figures that out and then compensates. So we can actually get pretty good answers from a stretch sigma type sampler. We can also get 10x speed ups at 3 sigma, 1000x at 4 sigma, 100,000x at 5 sigma compared to brute force. So it's really nice. And then it's also got a really cool self-verification algorithm built in. So that's some of the neat stuff that we're doing. That's all current work. It's still improving, still advancing. It's released 2 years ago, but actively working on it. Another thing that we're really excited about is called High-Sigma Verifier, where what we did here is we took our High-Sigma Monte Carlo algorithm that was sort of the thing we were most famous for, I think, at Solido, and we really put this on full autopilot. We put a bunch of smarts into it so that it was extremely easy to use. It minimized simulations even more, 0 manual tuning, 0 iteration. It just gave you the right answer the very first time. So the key thing, you know, if you look at the setup of this thing, there's nothing to it. You set your targets, you say, you know, which outputs you care about. You tell it if you want to, you know, go out to 6 sigma or 5 sigma or something like that. If you don't know, you just want to see what it can do. It can just go and solve whatever yield your circuit has. And then there's some ways of controlling variation. Hit go, and it just figures everything out. So it's actually all the cool algorithms and all the cool tricks are just happening fully adaptively under the hood. It's doing the right thing to minimize the number of simulations, give you the right answer. And when compared to our High-Sigma Monte Carlo, which is sort of, you know, previous industry standard, still industry standard in a lot of places actually, it saves a lot of simulation, and there's just zero iteration. It just gives you the right answer the first time you run it, which is really nice. I wanted to switch over to characterization a little bit here too and talk about what we're doing there. So the characterization problem that we've got is that we just got a ton of simulation here. So, you know, we might have 500 process voltage, temperature, extraction conditions, and VT families. It might be, you know, 5,000 standard cells in a library, including different drive strengths and so on, 10 arcs per cell, 10 measurements per arc, 7 slews, 8 loads. And then if we simulate all that, what we end up with, if you just multiply that out, we've got 14 billion simulations from that example, which takes, you know, typically thousands of CPUs several weeks. So this is already a big problem. What happened is we made this statistical. For our sequential cells now, we're actually, instead of just running one simulation, we're running a Monte Carlo analysis, which really sucks actually, because now we turn this problem that was already long into over 1 trillion simulations if you brute force it out, and it would take thousands of CPUs, you know, many years, maybe decades to complete just once, which we can't do obviously. So there's actually 2 major problems that happened. Of course, the characterization tool providers didn't say, well, let's just tell people to spend multiple years. They actually built algorithms to try and approximate things. It still takes way too long. With statistical characterization, we're seeing typically a 4 to 12 times increase in runtime compared to just NLDM characterization. And then we're also seeing lots and lots of errors from some of these fancy algorithms that are sometimes right and sometimes wrong, and the errors need to be caught and solved. So problem 1, generating timing model data faster. The problem here is, hey, let's speed this up. We've got a nice active learning approach here. There's a product that we have called the MLChar generator, which builds machine learning models, and it predicts out a lot of the data automatically. The way it works is you might just have a few simulations that you've run, build the model through. This is just a simple one-dimensional representation. If you imagine this happening across 5 or 7 or 10 dimensions, you get the right idea. So complex multi-dimensional surface models building under the hood. But, you know, you've got a few points, and it can build a model through it. That's what this dashed line is. It can run predictions. And here we've got some actual simulations of the predictions that are kind of in between here, shows kind of, you know, max error that you tend to see with this type of approach. It's really nice and tight. You can do this for delays. You can do this for transitions. You can do this for internal power, for leakage power. And one of the really cool things that you can do it for is for waveform data. So characterizers have not just numbers, but they also have shapes in the data. And we can actually do this for shapes, where we've actually simulated 3 waveforms, this one, the one at the bottom, and all the rest of these other 2 are just interpolated shapes, which is really cool. And you can see the dashed line is the guess from the system, and the solid line in this case, and in this one here, is the actual simulated waveform. So really interesting that we can do shapes. We had to develop all this technology. This was all stuff that wasn't off the shelf. We had to invent this. So lots of cool things we can do there. We can also use machine learning and active learning to find errors in big data. So we've got something called MLChar analytics. And what this does is it goes and builds machine learning models through existing data, and it looks for points that don't follow the model, and it can report those, and you can go solve them. First of all, you can see it really, really easily. You can find them. You can find, you know, thousands of new problems you couldn't find before. And this is really effective. If we look at what it's done, you know, this is all adapted from real production libraries that were fully verified. You know, it finds errors in pulse width, errors and setup constraints. These are supposed to be nice, smooth lines, you know, and you see these jagged things. These are errors in characterization. transition time errors. This is simple stuff too. This is, the fancy statistical stuff I was talking about. Hold time errors, setup time errors, Skewness. This is getting into statistical. You can find just these completely messy spaces where the statistical estimators completely break down in the characterizers. This is actual real production data from tier ones. So lots of problems that it can find and help squeeze out really quickly. This is stuff that would take ages and ages to find using brute force methods and manual analysis. And with an active learning approach, we can actually dive in and find these right away. So all kinds of different errors. So really the summary here is that active learning has been a great tool for us for solving a number of coverage problems in our space. There's been lots of really good benefits to SPICE coverage, and really some nice generalizable benefits, I think. So the problems that it solves can be quite general, gives us those order of magnitude speedups. It can target areas of interest and give us really good accurate guesses within tolerances, and it can produce really nice usable solutions where designers don't need to know anything. It can just be push button and fully adaptive. So I thought I'd just share this really good class of algorithms. Has been really successful for us, something that we've been able to use kind of as a general purpose solution to many problems in our space, and hopefully it's something that you also find useful and that generalizes. That's it for me.
The keynote is now open for questions. You're going to need to push the red button next to your name, otherwise we don't hear you.
Yes, Jeff, I had a question for you. It was really interesting looking at the slides toward the end there, I guess, in terms of all the different types of errors and things that you're able to find. When you find an error, how easy is it for like a designer to debug with that information to figure out potentially how to fix those problems?
Yeah, so for the people in the audience that have dealt with characterization before, timing characterization is actually really tough, because what causes these lumps here is usually an error in the simulator configuration that it's maybe you've got not accurate enough settings or something like that, or not enough time steps or something. A lot of the time it's a simulation error. So what you need to do is generate a net list, a SPICE net list, and then kind of iterate and figure out, well, what went wrong there? And what we actually do is you can actually click on any point in this tool, and it automatically will go and generate your net list for you, and then you can kind of play in that playground, which is really nice. So this saves hours every time you click that button. It's really hard actually to recreate the exact situation that caused these things. So we try to create accelerators for that. We've also got some technology that we're just working on right now, a little spoiler here, that automatically goes and corrects stuff at runtime. And so when it sees these errors happening, it says, well, let's just use the usual rules of thumb, crank up the accuracy settings, increase time steps, whatever we need to do, and automatically fix the problem so you don't actually get them in the first place, which is really cool. When you know there's problems, now you can actually go and solve the problems too. So we're doing both, trying to make it easier and just completely solve them automatically rather than leaving the long debug period. So that's something else we're trying to do. Thanks. Really good question.
So thank you very much for the interesting talk. I would like to ask about the verification part, because you mentioned about the self-verification part. So could you please elaborate on the self-verification part? What kind of methods verification has been used in that? And second part is that how do you ensure safety? Because you also mentioned safety critical applications.
So I heard the first part, which was about self-verification and how does that work. So I'm going to give an example. When we run our High-Sigma Monte Carlo, for example, this is one that's really simple. What we'll do is, what the algorithm does is it uses its machine learning model to predict the order of millions or billions of statistical samples in output space. So what we need to verify is that predicted order is actually correct. And what the algorithm then does next is it says, let's actually start simulating those in the predicted order from worst to best. So it starts simulating, it says, here's what I think is the worst, I'm going to simulate that. And if it's we don't know yet because we don't have anything to compare it to, but then we're going to take the one that thinks it's second worst and simulate that. And if it's actually worse than the one that thought was worse, well, then it looks like, hey, something's working. We can keep doing this. And we run, a couple thousand of these. It's not just we run 3 or 4. We'll run thousands, and we'll actually see, which is way smaller than millions or billions. We'll run 1,000 or something, and we'll see, how well does the predicted order correlate with what we actually see in SPICE if we run those. So we can actually see the algorithm working in real time. We can actually compare the predicted order with the real one, and usually there's some noise. It's not going to be exactly right, but what we can see from the noise is how much it's off by, and then we can also see, based on how much it's off, how many we'd have to run in order to find the actual, 6 sigma value. We can do that all dynamically, which is really cool. So that's one approach that we use. We actually think about this for every single context. We think about, how would a person really want to prove this out and verify it? What would they do if they had to do it manually? And we try to replicate that exact same kind of process fully automatically, really, really thoroughly, so that they can just kind of point to it and say, hey, look what this tool did to verify. So it's actually a different design every time that's carefully done on whiteboard. Sometimes there's generations of improvements with it, something we put a lot of effort into. There's no one silver bullet for it, but it's a really important part of producing production tools that people will trust. And then the second part I didn't catch.
So basically, I asked about the safety critical applications because you mentioned them. So how do you ensure safety in the case of statistical approaches? So, that could lead to some safety critical issues.
And I'm sorry, I missed it. Again, I'm just going to turn my volume up a little bit here. Can you try one more time? I'll try to listen a little more closely here too.
Yeah, sure. So basically, you mentioned safety critical applications, right? And my question is that when you do the verification part with statistical approaches, how do you ensure safety in this case?
So with statistical applications and self-verification, how do we ensure which part?
How do you ensure safety for a safety critical application?
Safety, yeah. So what we're doing in this space with SPICE and manufacturing variation analysis is what we're trying to show with safety, this specific to safety, is we're trying to show that there's enough margin. So let's say that you think you really want to demonstrate that you've truly got a 1 in a million failure rate. Well, if you had to run millions of simulations to do that, you wouldn't be able to do that. But with our tools, you can actually demonstrate that 1 in a million failure rate with 1,000 simulations. And so you can actually show that you've got the margin that you're proclaiming that you have, because you can actually now cover that whole space. So what we're showing is statistical margins. The other thing too that we show is that sometimes, if you're taking the worst case PVT condition, for example, and just trying to show statistical margins there, you might actually be missing what's really the worst, because what's worse at nominal is often not the worst case at statistical, because you'll get these long tails that happen at some conditions and stuff like that. So what we can actually do too is increase the statistical coverage to show that not only do you have your 1 in a million failure rate at one condition that we thought was the worst, but in fact every single condition we can cover as well, and show that you've got a 1 in a million failure rate or less across the entire process, voltage, temperature, operating type range. So it's really those two things that we do. Yeah.
Great. Thank you very much.
Yeah, you bet. Thanks.